Hello, everyone. Welcome to DFI's Impact webinar. This webinar is hosted by DFI's Driven Pile Committee to highlight developments, current practices, and case studies focused on driven pile foundations. If you have a topic that might benefit the industry, please reach out and volunteer yourself or volunteer one of your favorite colleagues to present on a topic. My name is Travis Coleman, and I work for GRL Engineers. So very quickly, all attendees will be automatically muted during the presentation. If you do have any questions, please use the chat function within the website, and I'll monitor those, and we will address as many questions as possible at the end of the presentations. So today we have two great topics. Jesse Rauser from the Louisiana DOT will discuss the DOT's experiences with pile foundation projects, and Robert Thompson from Dan Brown and Associates will present on large diameter open-end pipe piles. So Jesse, you have control.
All right, thanks, Travis. I assume you can hear me.
Yes, sir.
All right. So yeah, thanks to DFI for letting me air some of our dirty laundry. I'm going to present a handful of projects here where hopefully it's not a case of, man, how did y'all screw that up that bad, and more of a case of where there's some lessons learned and maybe some thought-provoking stuff, or maybe you haven't encountered something like this before and you see it from a different perspective. So I'm going to start off with project one. These are all anonymized to some degree. It's a 270-foot bridge replacement in St. Martin Parish. The piles were 30-inch square, up to 100 feet long, with up to 227-ton strength loads. And we designated one indicator pile for dynamic monitoring. And I'm not sure if everybody around the country uses the same lingo, but for us, an indicator pile is basically a test pile without a static test. And so it gives us a chance to do some testing and set our order lengths before we commit to producing piles. And so the soil conditions at this site were mostly clay with a sand layer down at about 95 feet down below the ground surface. Coincidentally here, that's the same as about minus 95 because we're at sea level more or less. And the piles were designed to tip into the loose to medium dense sand at the bottom of the borings, but these are still predominantly friction piles. We weren't expecting a whole lot out of the end bearing on these piles. Oh, sorry. It lagged a little bit on me. Let me see if I can get back to where I need to be. Okay. So indicator pile one was a 96-foot long by 30-inch square pile. The required nominal resistance was 425 tons. And so on these indicator piles, we typically do end of initial drive, 24-hour restrike, and 14-day restrike dynamic monitoring. And on this particular pile, after we did our cat web analysis, and built our pile setup curve, we're looking at about 60% of the required 14-day resistance. And you can see the chart on the right. Even if you project this curve out to 1,000 days, we're not even coming close to what we need. So setup's not going to save us here, and we really don't have enough data to estimate new pile lengths. And typically we're pretty good at designing friction piles in clay. So what happened here? And so we started by ordering a longer indicator pile, and I got notification of a change order due to a design error, which didn't make me very happy. So I started going back and digging through all the original design. And, the design profile from that initial indicator pile was already conservative, as you can see on the right. The green line was basically my strength profile for the design compared against the SU values from the borings. But we located some additional borings and plotted them alongside what we already had. And all of a sudden, we're not so conservative with our profile anymore. And then so if you take what we had and divide that by about 2, it kind of comes into line with the historical data as well. So we updated our pile models to match this new profile, and it actually matched really favorably with the previous PDA data that says we weren't going to get capacity. And so we drove indicator pile number 2, which was 125 feet long. So that put us about 16 feet deeper than indicator pile number 1. This was almost a year later, just with the whole change order process, it became a nightmare. And so we did dynamic monitoring on the end of initial drive and 24-hour restrike, and the cat web indicated that, within about a day, we hit our required nominal resistance. So, it's interesting here on the right, these piles set up at virtually the same rate. And really all we needed was to get a little bit more in bearing out of this pile to have the capacity we needed. But we initially grossly overestimated the side friction. And so I want to show another similar project. This was an interstate widening, an overpass that was almost 1,000 feet long. And on this one, we had 2 indicator piles. And right off the bat, based on the PDA, the indicator pile resistances were much lower than we expected. And so again, revisiting the design profile, you could, the yellow line here is what we designed, or what we selected for our design, compared against the SU values from our borings. And we're fairly conservative here. It's definitely not the mean. And so we found some historical borings and plotted them alongside the new borings, and lo and behold, the same thing happened. We're not conservative anymore. Again, multiplying the existing data by 1/2 seemed to provide better agreement with the historical borings. So we kind of rolled forward with this new profile. I think I'm lagged again. Let me give it a second. Okay. And so we basically went back and did dynamic monitoring, or we compared this model to our old dynamic monitoring, and you can kind of see the red line on the graph was the original target resistance, which we had no chance of hitting, and the yellow line here is based on a recalibrated model, when we took those historical borings into account. And interestingly enough, we're only 10 tons shy of the projected 14-day value in our PDA data the second time around after we recalibrated our model. So the lessons learned here was we went back to our laboratory and said, hey, can you review your compressive strength testing and reporting? Anybody that's used to doing pile design based on boring logs knows that there's a couple of different places where you could potentially introduce a factor of 2. But no errors or deficiencies were found or reported back to the geotechnical design group, especially in terms of unit conversions or swapping compressive strength with undrained shear strength. And so as a result, we, internally in our design group, we tried to place more responsibility on the engineers to get involved with the sampling and testing, because generally if you handle a sample, you should know, if you handled a sample that was twice as stiff as another sample. And so the idea is to get a better idea of what the site is before you even start designing anything by being involved in the sampling and the testing. It also caused us to put a greater focus on data management. And so, prior knowledge of those historical borings would have averted these problems entirely. And so now we do have some ongoing research where we're trying to locate and centralize our historical data. On top of that, we acquired a new CPT rig, 3-4 years ago, and we are trying to order CPT soundings alongside our borings on every project to whatever practical degree we can. And another lesson learned here is trust your dynamic monitoring. We could have easily said, hey, we don't believe these restrikes, but it turned out that pointed us in the right direction to solve these problems. And luckily we didn't order piles based on the original designs. The next project I want to talk about is a 200-foot bridge replacement over a creek in St. Helena Parish. There was 18 feet of scour up on these bents during the 2016 flood. So this was an emergency project to try to get this bridge rebuilt. We had 24-inch square piles up to 77 feet in length with 200-ton loads. And we had 1 test pile designated for static load testing and dynamic monitoring. Again, because I mentioned this is an emergency project, we were not allowed to get soil borings. We begged and begged, and project managers told us, no, you need to use what you got. And the 1971 historical borings indicated sand, clay sand, and silty sand with some gravel. And then we designed these piles to tip into loose to medium dense sand at the bottom of the borings. I say design with quotes because it's really hard to read these boring logs, so we kind of did our best. So test pile number 1 was a 77-foot long by 24-inch square pile. During the static load test, the reaction piles failed at an applied load of 280 tons. And I have that number highlighted, so keep that in mind. That's important for the next couple slides. The reaction frame was supported by 4 22-inch steel pipes. Those were embedded about 90 feet below the mud line. And then after the failure during the load test, the contractor, he decided to add length to the reaction piles. And in the meantime, we decided to make some supplemental CPT sounding, since all of a sudden the emergency job wasn't a rush anymore, and we had time to go ahead and get some geotechnical data. So we did confirm the predominantly sandy profile. And it was interesting, there's a lot of variability in the tip resistances. We were able to push these CPTs to 150 feet, which typically we don't expect to be able to do that in a sandy profile. So here's the first load test that we did on this project. Keeping in mind that 280-ton load, we basically, I'm sorry, this is the second load test that we did. So, but anyway, keeping in mind the 280-ton load, the second test pile failed. Well, if you look at Davison, we're about 100 tons below the required resistance. And we did not make the 280-ton load that we made the first time when the reaction system failed. And so now we kind of have two problems. A, why did the model overpredict so much? And B, why did we lose resistance between the two tests? Because we were pretty much on the elastic line when that first test, when the reaction piles popped out at 280 tons, and now we can't get it. So I went back and took a look at, let's look at the reaction piles and can we back calculate anything off of that? So we don't know exactly when or how they failed during the test, but you can make an assumption that at some point in time, either 2, 3, or 4 of the reaction piles were carrying that 280-ton test load when one of them failed, at least one of them. And so, using that, we can estimate the load distributed to each pile and back calculate the average fee along the embedded pile length. And, it's interesting here, if you do all the back calculation based on how much pile is embedded, even if only 2 of those reaction piles carried the test load, then the average fee along that embedded pile would be about 20 degrees. And if you look over, the kind of the middle vertical line would represent if 3 piles held the load, you're still looking at something less than 15 degrees, which is insanely low for what we would expect these piles to have as a side friction or a fee value for the side friction. And so kind of the lessons learned here was first you want to talk to the guys with the green hard hats. Those are usually the new hires. And we got one of the guys to admit that, yes, we did lengthen and drive our reaction piles with a vibratory hammer, and that's forbidden in our spec. We also know that our published correlations in most of the literature overpredict fee in soils with high fines content, especially in Louisiana. And so on most of our projects, we will semi-arbitrarily reduce fee when we see a high fines content. However, the historical borings did not have -200 testing, so we don't really know what the fines content was on these. So we're thinking that the low test pile resistance, the second time around, was probably due to dirty sands plus vibratory pile driving being done just adjacent to the test pile to prepare for that second loading. And so another lesson learned here was I think geotechs, we need to do a better job conveying the importance of our recommendations. And this can be difficult since we deal in a lot of risk-based stuff. We deal in a lot of maybes, and we don't deal in yes, no's. And it makes it hard to be firm in saying, hey, I need new borings for this. I got to have borings. How do you convey the risk of designing, from old borings versus new ones? And, similar to that, our specs already forbid the use of vibratory hammers. How do we enforce these things when it's very hard to prove the impacts? It's rare that we get a project like this where we can kind of back calculate those types of things and say, hey, we're pretty sure the vibratory screwed us up. I want to change gears. The third project I want to present is a 500-foot-long river crossing in Richland Parish. We had 2 test piles designated for static load testing on this and dynamic monitoring as well. So the soil conditions are generally sandy here. And the piles were designed to tip about 60 feet down into the medium dense to dense poorly graded sand. One thing I want to note is the fines content on these borings to kind of connect to the previous project, the fines content was generally less than 5%. So really not a red flag in terms of a dirty sand. But the first test pile was installed to 33 foot of embedment. That includes the casing that was excavated to account for scour, friction losses just due to scour. Did dynamic monitoring at end of drive in 24 hours, and then the cap WAP shows about 50% of the required resistance at that point. And, as expected in a clean sand, there was virtually no pile setup. And so looking at these results, we said, look, we're never going to get capacity on this pile. There's no point in loading this. So we just decided to forgo the static load test. I will say this was a consultant design, not to point fingers, but it ties in with the lessons learned on this. And, the fines content on this project was less than 5%. There would have been no red flag at all. The independent review, if you follow NHI manuals and AASHTO by the book, I was able to match the consultant's pile lengths within about 5 feet. However, internally, our institutional knowledge says that we do have problems in alluvial soils in eastern Louisiana, specifically in the Florida parishes, and then between the Ouachita River and the Mississippi River, which I've highlighted on the drawing here. And, typically our institutional knowledge will lead us to reduce our fee angles in these areas, 10 to 15%. It's arbitrary, semi-empirical, but it's something we know about. And so typically we'll do that. But in this case, that wasn't done for the design. And so the new pile order links for the new test piles resulted in a change order for a new crane. The contractor said, well, I can't pick up this longer pile. And so the change order was exorbitant, and we basically canceled the project and relet it. And so that brought up some questions that I had to answer to the project management people. And one of those was, well, should a consultant be expected to have the same institutional knowledge as the department? And I don't know the answer to that, but we are lucky in that as the department and the owner, we have the benefit of statewide experience on all kinds of construction projects. We see all kinds of stuff. Is it fair to expect your consultant to kind of pull those same arbitrary empirical factors, from their experience? I mean, or are they expected to know as much as us? I don't know the answer to that. But how do we provide design guidance for a reduced fee? Because we don't even know the extent of those sands. We don't even know the exact issue. Maybe sometimes it's fines content. In this case, it wasn't. Maybe it's the angularity, how rounded the particles are. Maybe it's something else altogether that we don't know. But interestingly enough, I went and pulled an old historical design guide from my previous job and the local practice here 50 years ago. The sheet here is dated 1972. They recommended reducing Peck, Hansen, and Thornburn by at least 5% and up to 25%. And that's interesting that this problem's been kicking around for half a century, and we've kind of made the full loop and forgotten about it again. So the lessons learned here is that the fines content is not the only red flag for pile design in sands. Typically, I think as geotechs designing piles in Louisiana, or in the South at least, we look for that, but there's other things that can cause problems. And so internally, we did have a general feel for this, but how do we improve our approach? How do we preserve the institutional knowledge that local firms knew of 50 years ago? How do we communicate that to our consultants as well as internally to new engineers? And when it's kind of arbitrary, how do you manage that risk of saying, well, we arbitrarily reduce our fee angles by 10%? That's not, I mean, it's kind of procedural, but it's how do you tell somebody to do that when you can't really back it up? So we initiated a research project to supplement this knowledge with modern testing. That research is still ongoing, and we've acquired some static load test instrumentation, and we're trying to instrument more piles, especially in those kind of that Bermuda Triangle area where we know we have trouble with sands and we don't exactly know why. And then another lesson learned is we modified our standard specifications to require contractors to bid equipment capable of driving piles 20 feet longer than the plan lengths. On this project, that may not have helped, but the idea here is to give us as geotechnical engineers more freedom to use the observational method through test piles and indicator piles as intended. Another project I want to talk about real quick consisted of 2 bridges. One was over the Red River. It was a huge bridge, and one was a railroad crossing tied to that project. And I'm going to talk about the railroad piles here. Those were 30-inch square up to 91-foot length and close to 300-ton design loads. And so we had 3 test piles on the job, and one of those was instrumented. And you can see here the profile is variable sands and clays. And the piles here were designed to tip into the dense silty sand near the 55-foot depth. So test pile number 11, we only had 3, but I'm not sure why we called this one 11, was a 60 by 30-inch pile. It was instrumented with 4 levels of strain gauges, driven to a tip elevation just above the very dense sand. We wanted to see what we'd get if we didn't tip into the sand. And it was loaded to failure with a Davison load of about 479 tons, which exceeded what we were looking for in the model by 165 tons. So, we knew this pile was adequate without having to tip into the sand. And so now the question is, because the pile is instrumented, can we take that strain data and extrapolate alpha and side friction to other piles and design those? And so just here quickly, I want to show N values and SU values versus elevation. The squares are SU and the blue triangles are N values. So, essentially you've got some stiff clays, and then eventually you get down into some pretty dense sands. So looking at our unit adhesion from the strain gauges, it kind of matches the trend from the borings in that it gets stronger as we get down to elevation 60 and below. But, interestingly enough, we have this zone that had really low side friction, lower than expected, and it basically back calculates to an alpha of about 0.2, which we thought was a little bit too low. And so the PDA with signal matching was done for a 24-hour restrike and an after load test restrike. And if you take this unit side friction from the cap WAP, it matches the unit side frictions from the static load test really closely, and kind of corroborates what we thought was a problem. And so we asked around, and we found out that the contractor on this one had pre-bored with an oversized auger, potentially reducing the side friction in the pre-bore zone. The lesson learned from all this is that our standard specifications were modified to require the contractor to furnish the pile driving logs. At the time of this project, our districts had to furnish the logs, and sometimes they didn't come around for the test piles. They didn't maybe see those as important. And so ultimately the pre-boring operation was not documented or reported to the design unit. So we didn't know about it. And again, to make the point again, trust your dynamic monitoring, trust your instrumentation. But with the caveat, yes, we got lucky. In this case, the cat WAP unit side friction tended to match what we saw in our in our instrumentation, our strain gauge instrumentation. But I'm not trying to say that cat WAP unit side friction distributions are meant to be accurate. It worked out great here for us. Another project was a bridge crossing in West Baton Rouge Parish. It had 15 pile groups, ranging in size from about 16 feet square up to 62 by 44. And those bigger ones had loads up to like 6,000 tons. Supported on 18 to 24-inch square piles and up to 85-foot lengths. This one's interesting because within a few months after the footing pour, the contractor notified us that the piers were settling. And so what you're seeing on the right, at the time we were notified, that's about how much settlement data we had. And so what you're looking at here, the reddish orange points are survey points from the footing, and the green triangle is the planned footing elevation that it was supposed to be poured at. And so you can see there's a couple things going on. There's a gap in the survey. Here it's about 50 days. In some of the pile groups, the gap in the survey was up to 100 days. And so at the time of the notification that, hey, we've got a settlement issue, we had as few as 8 survey measurements with a big gap. And then I will say that, we looked into this and found out that the footing elevation was not surveyed at the time of the pour. So the contractor assumed that it was poured at the plan elevation. The first survey was made a few days after the pour. And in some cases, that first survey point showed up to 1 inch of settlement in like 3 days. In another case, it showed that the footing went up. But this is the data that we were supplied to look at and to try to make decisions, because, at this point in the game, everyone's on high alert because it looks like it's a bad situation. But based on that limited survey data, any number of projections could be reasonable. So, taking a typical, time rate model, you could bend that data to go, say, hey, this is going to settle 2 inches, it's going to settle 3 inches, it's going to settle 4 inches. And I could have kept going, but I figure this illustrates the point pretty well. So the first thing we did was say, hey, is the survey adequate? And so they got a third party to go back and look at the survey data, and there were some sources of error found. In particular, one portion of the survey was found to have an accuracy of about 3/4 of an inch. However, the survey was found to be adequate for its general intent, which was not forensics. So keep that in mind. Is what us geotechs may need to make our decisions is not what the contractor needs to do his job necessarily. So the kind of survey thing was put to bed, but at the same time, we're sitting here like, well, how are we going to make heads or tails of this without better survey data? So we kept asking, and we requested that survey measurements be furnished weekly. And still, what I'm showing here on the right is a year of survey measurements, and still, depending on how you want to project the data, it could be compatible with multiple projections through this set of data points, depending on how you want to do it. So what if we got to thinking, what if you treat the pier like a large scale consolidation test? Because we know when the loads were applied, we know when the footings were poured, we know when the columns were poured, we know when the girders were added, we know the magnitude of those loads. There's a little bit of fuzziness in the time because some things, they don't happen on an instant. But what if we assume that C sub V and the drainage path remain constant versus time? That's not 100% true, but for the accuracy of what we're trying to look at, it's a good assumption. And then what if we take all this and develop an equation for degree of consolidation versus time, knowing when those loads were supposed to be applied? And if we do that, then we can basically curve fit that degree of consolidation curve for U equals 100%, and basically it's almost like signal matching in a cat wat, where we have a model and we're trying to match it to the measured survey data, at which point, if the model's true, then we know our total settlement becomes true. So interestingly, you can look at this set of data on the right and kind of mentally say, okay, I think I can draw a line through that with, in my head and make sense of it. So this is what, on this particular one, this is what the model shows. So if you step backwards through the data, which, it's kind of flatlined at this point, so it makes sense to kind of start there and go backwards. The model should cross at a settlement of 0 inches. That's the whole point of the model. And so if you believe this, if you believe the model and all the data, this basically suggests that footing was constructed 3/4 of an inch off of the planned dimension. Some of these other ones were off by 1.5 inches. And so, the point here is, if the loads, the dates, and 90% of the survey data are accurate, then those initial points on the survey either incurred significant error or are measuring some other movement other than the pier movement due to consolidation settlement. And so kind of the lessons learned on this, it took us a whole year of data to kind of get to a point where these models started to match for all the piers. But interestingly enough, I think the lesson learned on this has the most to do with communication. And so as geotechnical engineers, we need to do a better job communicating the observational method to other disciplines, because I don't think a lot of these guys understand what goes into that and the limitations of that and the needs of that. So, we had a need for better and more frequent survey data that was initially ignored. A lot of decisions were made before the survey and settlement data could even be fit to a model. It took months to receive accurate load and data information. And again, like I mentioned on a previous kind of punchline on one of these projects, I think it's because geotechs deal with a lot of maybes and risk-based, hypotheticals, as opposed to a yes, no. And so it's very difficult to come along and demand something that's going to change a contractor's schedule when we can't guarantee an outcome. If we say, I need you to stop for this long, well, they can assign a dollar value to that. And as a geotechnical engineer, how do you turn back around and assign a dollar value to whatever risk you might be trying to mitigate? I think that's really difficult to, we're really up against it in that regard as geotechnical designers. And so I think we need to also communicate the limitations of what we do. It's difficult to predict the magnitude and the time rate of settlement as a Class A prediction. And so knowing this, knowing that it's hard to predict settlement, how can I then turn around and convince somebody else that those initial survey points are wrong based on my settlement model? It's food for thought, but I'm pretty convinced that, going back and looking at this, that the rest of this model is pretty good, except for those initial couple of points. And then for the last project, I'm gonna get through this one really quick. It's a 450-foot bridge replacement in Tangipahoa Parish. The piles were 36-inch open-ended steel pipes up to 110 feet in length with 258-ton strength loads. And we had a test pile with static and dynamic monitoring. And let's see here. So this is our design profile. The fines content was generally less than 10%. So again, we didn't have a huge red flag in terms of dirty sands. And these piles were designed to tip into the medium dense sand near the 90 to 100 foot depth. And the assumption was that these piles would plug. Here's our static load test. So it was 100 foot long by 36-inch large diameter open-ended pipe pile. I will say that LADOTD's experience with these pipes is limited, and they went generally unused until within the last few years. And we kind of started using them on emergency projects where we knew we could potentially drive them, test them, weld some more on, keep driving. And there's things we can do with these that we couldn't do with concrete pipe piles. Some of the dynamic monitoring on the test pile gave us some funky data due to some access and clearance issues, but still the limited results from that suggested we did not mobilize the plug. So we loaded it during the static load test, and we failed to meet our required resistance by about 200 tons. And so similarly, looking at the PDA data, we don't really project to get capacity on the monitor piles. So we recalibrated our model based on the plugging situation, and still on the monitor piles, we're showing that we're not going to hit capacity for almost 100 days. And so it looks like we overestimated our capacities even after revisiting the model. And so kind of the lessons learned here are regarding the pile plug. The future designs, we're not going to assume that these piles plug anymore. We learned a lesson here. And dynamic monitoring should definitely be used with care. You may not mobilize that plug dynamically. And so, another recurring theme is I think we probably need better side friction estimates in sand, especially when you start to approach that, anything above a 5% fines, at least in the soils that we have here. And hopefully that segues well into what Robert's going to talk about. And that's all I've got. Appreciate it. Thanks, everybody.
All right, guess I'm up. Thanks, Jesse. That was great. I really enjoyed that. That's a hard one to follow there. A lot of good gems and nuggets in there. All right, I'm going to present a little bit, a really high level view about open-ended piles for transportation structures. There may be a few here that saw some version of this back at the Southeast Transportation Geotech Conference several years back, or something in the Midwest that Dan gave. But it's updated a little bit, but it's still just a really high level view of the issues that we find in using large diameter open-ended piles for transportation structures. And by no means will anybody be an expert in design of these piles by the end of this presentation, but hopefully you'll go away with some food for thought, some things to consider if it is new to you. Like Jesse said, for LADOTD, it's really coming in within the last 5 years, and we've seen that in our practice, and I know others that practice similar to us around the country have seen the same thing, that they're being turned to more and more often by states through the design build process, or just from the effect of availability or ease of construction and verification. Like Jesse said, you can modify them in the field a lot easier than you can, say, a concrete pile. So let me move on and get going. Oh, there we go. Finally caught up, woke up. Okay. I put in here some references, and you'll be able to see these later, but the main references for some of this information. A synthesis that Dan and I did back in 2015 for the collecting information on how the states were starting to handle these type piles. There was a research project done for FHWA that Catherine Pedic at Shannon Wilson headed up, and has a lot of good information, especially some real good analysis of trying to calibrate resistance factors. So that's a good reference. And then, of course, the GEC 12, Federal Highways Design and Construction of Driven Pile Foundation Circular, has great information in it for designing these piles and in every driven pile. And the upcoming new revised driven pile course, I would expect to have at least touch on large diameter piles. So what do we mean by large? 36 inches outside diameter or larger is what we, as an industry, have kind of settled on for when we talk about large diameter open-ended pile. That's what we're talking about. And they come in the two flavors there: steel, right, our tubular steel pile, and our pre-stressed concrete cylinder pile. And the end is open, as you see, but we'll talk about a little bit about efforts to try to generate a plug by sort of closing it off, if you want to describe it that way. When are they used? And a lot of the things, they're common to all of our deep foundation types. We can see that there. So as the panel we were talking about earlier, I try not to say advantages, disadvantages. It's just, these are things to think about, or these are aspects of these piles, since they can often be attributed to or described for other types of foundations. So high lateral load demands, especially extreme event loading. Sometimes we turn to drilled shafts for that, or we could do a really big footing with a lot of H piles, but we turn to the larger diameter foundation units in these situations because we should be able to use fewer of them and have a smaller footprint and carry the same high lateral load demand with a tighter footprint foundation. Same thing, high axial demand and deep, weak soils. If we can use fewer elements, that maybe we can mobilize that resistance quicker and then be able to get in and get out of building foundations, the better off we are on the project. We could use the large diameter open-end piles like we would a drilled shaft, where we would on a small bridge with small piles. We could use a pile bent rather than a footing and the associated cofferdam. The delivery, handling, and installation for marine construction can be a little better in cases than some other piles, but it's especially when we're talking about being able to splice in the field, do things like that on the steel piles. But the larger diameter concrete piles, marine construction, float them in on a barge, have the right size crane to lift them and start driving. And we can support a significant unsupported length due to scour, liquefaction, marine conditions, just like using a large drill shaft, because we have a more robust pile section. So what are the unique challenges? Jesse already talked about one of them, and some people might say that is the challenge with large diameter open-ended piles is, when does the plug form? Does it form? When do we mobilize it? Can we mobilize it during testing or not? Can we sort of force it maybe, or really force it to mobilize? All of those things have to be considered by the design engineers, and I think that's what makes designing for these piles challenging as well as interesting. And there are some potential for installation difficulties, damage that's not like conventional bearing piles. Especially with we'll talk about one on a little brief case history about the concrete piles. That yes, driving concrete piles is always concerned about overstressing the pile, but the cylinder piles have a little bit more unique issues, and the same thing with our steel pipe piles as far as damage to the ends, and just the large diameter, large piles do make them a little more difficult to install, but contractors have the equipment that can make that seem like it's not that difficult. The soil column, we'll look at an illustration here in a little bit. That soil column or the plug is going to behave most likely differently during driving or dynamic testing compared with static loading. The pile is able to move a lot. I guess you want to use the word quicker. It'll move a lot easier than that plug and the pile trying to drive it or drag it down with it. So you have some inertial effects of how the pile can very quickly move under the blow of the hammer versus the dragging that plug of soil with it. What is our axial resistance from internal friction if we're if it's plugging or not plugging, what kind of friction do we have during driving, and then later once we load it statically. At any large diameter, whether it's a pile or a shaft, but the piles, that verification of nominal resistance is more challenging, and it's a lot more expensive than a load frame on a 24-inch concrete pile or an H pile or something like that. For those that may not be familiar, let's talk just a little bit about how these piles are manufactured. The steel piles are either spiral weld, and that's where they're going to do this continuous welding on a spiral as a steel coil is unwound. Maximum thickness is usually 1 inch. And as they unwind it, they will weld it and weld it together. Very cool process, and be able to do that continuously. The other option, or what was the option until spiral weld came along, was the rolled and welded. Just take plate, roll it, and weld it. The good thing about rolled and welded plate is we can get pipes greater than 1 inch. So you could do 1.5 or even 2-inch wall pipe. Just push the limits of your manufacturer. For our concrete pipe piles, they're going to be either spun cast or bed cast. The segments of them will be pre-stressed, and then they'll be put together in post-tension. The spun cast is a process where the form and the reinforcement, the pre-stress, everything's put on basically a centrifuge. You can see a big set of rollers there, and spun around. The concrete's introduced in the middle, and the centrifugal force pushes it all out to the outside, slings it all. If you want to just use slings it to the outside, and that force helps consolidate the concrete. But they can also be bed cast in a traditional bed cast way of placing concrete in a form with the pre-stressed tendons in there, and complete the pile in that manner. I thought about it yesterday. I didn't have a good picture showing the post tensioning cables, but you can see there in that lower picture the holes there on the end. That is for the post tensioning cable. So it'd be like putting the segments together on a precast segmental bridge. Run the post tensioning cables through there, put the fancy epoxy adhesive in between, and put them all together and post tension them real tight into the lengths that you want. And the diameters of those are usually in the 36 to 66 inch range. They could be the wall thickness 5 to 6 inches, and they come in usually 8 to 12 or 16-foot sections, and then they can be put together in the lengths that are needed for the project, and trucked or shipped by barge to the project site. So here's a simplified illustration that Dan came up with. Dan Brown came up with, and we put in. At least I'm accredited it to him. He may have had inspiration or reference another, but it is in the synthesis report that we did, and also in the FHW research report, trying to illustrate that difference of how the pile behaves, or that plug behaves, in a very simplified illustration. During driving, or during maybe static loading. And on the left, we're showing where the plug, too much coffee today. The pile is behaving such that the soil inside is acting plugged. And so as the pile moves, the plug is moving down with it. And so you're getting that resistance on the base of the pile, and that side resistance on the outside. A lot of times during driving or during our dynamic testing, our restrikes, that we don't have enough to for that plug to mobilize. The loading is happening too quickly, so the pile is moving down relative to the soil inside. It's not behaving plugged, even if later under static loading it does. And so the resistance to the pile moving down is that side resistance on the outside and on the inside, and of course any base resistance on the perimeter of the pile itself. During design and during static loading, if we're not going to get plug development, that's going to be our resistance that we'd be using for design. Looking at my time here. We have our steel, but let's talk about the steel piles very quickly. Sorry, I had a reminder pop up. Should have turned those off for the meeting. Tip for everybody: turn off your reminders. Base resistance of steel piles with using driving shoes, something to keep in mind. You don't want to have that happen that you see down there. And that can happen even with a driving shoe or a reinforced toe. There's always those issues of driving piles too hard, controls on how the contractor does that. The conditions, subsurface conditions. If we have sloping rock, we can't avoid that. It might, we've got to just be aware of it and take care of those things. But the shoe itself, if we're using a shoe, we do have to keep in mind as designers, all right, how is that size relative to the pipe pile itself? Does that increase our outside diameter and create that area where we've disturbed the soil, and we may not get relaxation to where it gives us the full side resistance, or we might. And same thing on the inside. Are we making it easier to drive? Are we losing that possibility of mobilizing the plug or partially mobilizing it during static loading? Vibratory driving and splicing. Jesse gave a good example of vibratory driving for the reaction piles. Same thing. If we do allow vibratory driving to begin a steel pile, and a large diameter pile especially, we have to make sure that that's clearly called out when that can happen. If it's been designed such that we're neglecting, say, the upper 40 feet for scour or other things, then it may be okay to go ahead and vibratory drive the first piece to that distance and then impact driving. But we have to have control of that through our specs and through our design controls. Splicing can be done in the field, but the larger the diameter, the thicker the plate, the much more difficult that's going to be as far as time. How does the contractor do that and getting good quality control? And what is the effect of our length on our behaviors and actual resistance? Do we have reduced side resistance, that remolding I already talked about, or friction fatigue? And what is our elastic compression during driving? The much longer piles we get, we have a whole lot more elastic compression that could occur. We just have to account for that. And Jesse touched on that time dependency, or talked about it, the time dependency of axial resistance. It is different for something that's open-ended versus our closed-in small diameter pipe piles, or our solid concrete piles, or even in our H piles as well. So how do we characterize that? Do we have some information we can get, or load tests or other case histories, or is it we need to establish that ourselves for our project? And then some of these things I'm talking about, you may think, well, Robert, here in the Midwest, we drive these things to rock. Some of this is not, doesn't apply. Yep, that's right. Driving them down to rock, we're just trying to get good in bearing on the rock, but we still have the other things to be concerned about as far as quality and behavior during driving. Our resistance and our dynamic load testing, mention that model. How do we model that? We need to make sure we're accounting for that inertial resistance of the soil plug or column. Is it fully plugging during driving or partially plugging? We were talking a little bit beforehand, the panel, about inserts to promote plugging. There's been some projects where that has been attempted. One that came to mind was one that Kentucky did up on the Kentucky Lakes project. Not seeing a lot of success with that, and it can be difficult to model and to measure dynamically. Very hard to make sure that you get a stiff enough plate and everything stay connected well, that you definitely have that plugging occur and don't just rip your plate out and you're just where you were started. Residual stresses have to be accounted for, especially in the manufacturing process. There could be some significant residual stresses in the pile. The biggest thing, especially on the large piles we're driving to rock, is those limitations of the hammer mobilizing the resistance, and that's common on any really highly loaded large pile. We just have to be cognizant of that, and what are we going to be able to show dynamically, and how does that impact our design and acceptance? And we have to pay attention to that detection and avoiding pile damage. Well, how does that large diameter and where the strain gauges are, how does that in it? We have soil in the middle now. How does that factor into the data we're getting and being able to recognize pile damage? Our concrete piles, well, that's a little bit different. Some of the same things. That volume, though, of the pile, that ratio between the concrete pile and the steel pipe pile, we've got a lot thicker wall because we're casting that 3 to 5 inch thick wall. And so how does that change that frictional resistance on the inside? How does it change the potential for plugging in the soil that we're dealing with? There is a potential for soil bulking inside the void, especially in marine projects. The case history at the end from Florida that I'll I'll touch on. We'll show. We'll talk about that and talk about the hoop stresses that could happen, or water hammer that could happen inside of these piles, and how do we deal with that in our manufacturing process and during construction. And just a reminder, all of these things I'm talking about, they aren't necessarily unique things that we or I have seen in our practice. It's what we've gleaned in our in that census report, and talking with other practitioners of the things that they've seen, and there are papers and case histories out there that touch on these topics. And I encourage you to dig through DFI One Mine and some of your other sources of finding these resources. Again, I already mentioned that the plugging versus mobilizing the cross section. We've already got a really big cross sectional area compared to steel piles that we can take advantage of, and so then that becomes part of us as the engineer. All right, do I need to count on that plug in the middle or not? Or if I do or want to, how do I characterize that? And driving, dynamic testing and driving concrete piles, management of our driving stresses is always key. We want to make sure that we don't overstress the concrete pile, and especially our tension stresses and easy driving. And when we're doing marine projects, we have a lot of easy driving, especially at the beginning. And that just comes from good specs, good contractor practices, and good inspection practices to make sure that we don't inadvertently overstress the pile during initial driving. And splices, they're rare. They can be done, but concrete pile, it becomes more difficult to do a splice in the field, just because we're now changing that pile and how it behaves from its manufactured condition. All right, we'll talk about design for axial loading very briefly. We're going to use our driving resistance. That's what we get. The static computations, they're just our guide for estimating length. There are manual in the FHWA manual and other references. We have our clay soils, our sandy soils. CPT data is a good tool, and as Jesse was talking about, they have started using the CPT or trying to get CP data with every project. And then there are some that are very specific to pre-stressed concrete piles. FDOT has a method for dealing with concrete piles. The stated practice from the offshore industry, the API method, which is in GEC 12, is that stated practice for offshore industry, which is mostly metal piles, has a long history of use. There's some slight differences from the FHWA methods, and they include some CPT-based methods, but we and several other practitioners have found it very useful to be using the API method for these large diameter piles, since its methods and calculations are based on their experience with large diameter piles, or mostly large piles, rather than a lot of smaller piles and a few large diameter piles, from which the methods we have for transportation within the FHWA guidance are based on. Resistance factor, if we're doing transportation projects, all about LRFD and resistance factors. The guidance and AASHTO don't specifically say, hey, do this differently for large diameter piles. They're based on mostly that NCHAP report that mostly consisted of smaller diameter piles. And if they were large diameter piles, they weren't documented separately. The FHW report that Catherine and her group did and published in 2020 has some really cool results of a resistant factor calibration analysis that they did. And if you're a data geek and really like to dive into things like that, it's some really good reading for you, and a reference and a tool that you can use. Lateral loading, serviceability. There's really nothing magic or nothing different about these than other types of deep foundations. We do need to make sure and consider that contribution to lateral stiffness, that plug, a concrete plug, is going to in the top of a steel pile. The smaller diameter concrete piles, maybe not so much. But if we're talking about a 60-inch diameter steel pile, we have that full of concrete for our connection to the cap. That's a lot of stiffness that we can rely on. And we also need to think hard about how does the soil plug contribute to axial stiffness if we're counting on, or we have that soil plug developing. Most DOTs are using the FHWA methods. A few have adopted API or a slight modification to that. The Nordland method in sands is pretty typical. The alpha in clays are the most common. And states are beginning to develop their own resistance factors or calibrate their own resistance factors, even for large diameter piles. But pretty much most people still rely on what is in AASHTO as far as the resistance factors they're going to select for design. Wave equation analysis is, of course, what most people are, what everyone's using for and high strain testing for our verification. Load tests are very common, but those can be anything between static, rapid, and dynamic load tests. Not as I was telling Travis earlier, dynamic testing is what we use, and it's great. We just have to realize that the larger the diameter gets in these open-ended piles, and we all realize that. And there's a lot of great papers out there from the dynamic testing folks at GRL and others that illustrate that we've got this to think about. It's a concern. How do we treat it, and how do we deal with that within our models? All right, in the 4 or 5 minutes I've left, a couple of quick case histories, really just to highlight some of the things that we've seen, and how for the large diameter piles. One's a pipe pile, steel pipe pile, and they were selected due to concern, or selected for seemed to be the best foundation type. We could drive these to rock, but we had to worry about vibrations on the existing structures. And how do we show that reliability and demonstrate the pile resistance so we can show that increased reliability we felt we'd get from these foundations? They were 42-inch diameter piles, 1-inch thick wall, where we had the ship impact loads or barge impact loads, but the remaining of them were 7/8 inch. All of them were driven to bear on rock. We did some statodynamic tests and demonstrated up to 4,600 kips on the 1-inch wall piles and the 4,200 kips on the 7/8 inch. The deflections were about 2 to 2.5 inches and a permanent set of around 1/4 inch. The dynamic test, we were able to mobilize up to 3,500 kips, but that was just the fact that that was the maximum we could do with the hammer that we had. Not that the piles couldn't get there, or if we could have somehow gotten a bigger hammer, but that's what we could mobilize. And so the dynamic tests were used as our basis to design. And you say, well, Robert, well, if that's the base of design, how are you going to show that with your dynamic testing? Well, they were used on production piles to demonstrate that we got good seating on the rock, the piles weren't damaged, and it showed the hammer was performing as intended. So that gave us the confidence if we met that, then that dynamic resistance we're showing, which sure, it was lower than the statdynamic resistance, but we know we have a good pile and that we can count on that statdynamic resistance for our design. St. George Island in Florida, I was not a part of this project. Dan was a consultant on it at one point. Is a long bridge going from mainland Florida to St. George's Island, one of the coastal islands there in the Panhandle, and a really cool bridge. A lot of load tests that they did. As you can see there, several statdynamic and static load tests and a lot of dynamic tests on these concrete piles. And Kemp and Mouchard published a summary of the results and of comparing the static to the statdynamic to the CAPWAP, and everyone felt there was reasonable agreement. Yes, some of the dynamic tests were lower or more lower. Can I say that? More lower than some of the others from the static dynamic, but they were able to get a good assessment of, all right, if this is what we're seeing dynamically, then we know that everything's good with the pile and we're going to get the resistance we need out of it. But here, longitudinal cracks were observed in about 7% of the pile within 3 to 4 weeks of driving. And some of you may be very familiar with this project. But it was determined to be water hammer from the buildup of that fluid soil inside the pile anus. As they were driving, that sand there in the bay became more fluid, and so you had pressures build up. And so you've got pressure building up and being from the driving process inside that column of fluid. And what a column of fluid doesn't compress, does it? So started to get all of that stress going out towards in hoop stresses or lateral stresses inside the pile, and resulted in cracking. And so to keep the project moving, what they did was they elected to monitor and clean out that plug and soil column so that they wouldn't get any future cracking. The FDOT details now have ports that allow for some of that pressure to be able to bleed off or vent off during driving. But it's something that they know could be a potential problem and they need to look at. So right on time, right at 1 o'clock, time for our questions. We're seeing more and more dynamic or large diameter piles in our transportation projects. There are there's my advantages and limitations I didn't edit out. There are things we have to think about, and whether they become an advantage or not to us, that's going to depend on our project. And there are some differing engineering concepts we need to think about in order to design them and to accept them in the field. And that's it. Travis, Jamie, take over for our Q&A.
Thank you so much, Robert. That's great. I have a few questions here. First, Jesse, thanks so much for pointing out the difficulties of dealing with answers that aren't necessarily absolute every day in our work. I have a question. Was this is case study 1? Was the design based on UU triaxial tests? Or what was it based on?
Yeah. We pretty much everything we do, we require UU triaxial on cohesive samples. So yeah, it was based on that. And then just to kind of follow up with the rest of that question. So, you know, it says, does LADOTD have experience with other methods for measuring SU, i.e. laboratory, mini vein and field vein, or other testing? And part of, you know, one of those lessons learned that I put was to get our engineers more involved in the sample handling and classification prior to it going to the lab. And the one of the things we implemented was having our guys run one of the little mini Tor veins on all of our soft samples just to have some kind of a backup. But in terms of, you know, field measurements, typically if we've experimented with a field vein and maybe didn't have the greatest results. And so, you know, I would say for us, the majority of our shear strength development is either CPTs in clay or UU testing.
Yeah, thanks. For case 1 and case 2, what's the reason for the discrepancy of the soil strengths from your soil borings? Wouldn't you think that your newer borings would be would indicate weaker soil, maybe?
I think it's probably something procedural in terms of I think it's an error in the reporting or the recording of the data. You know, the fact that we were off by a factor of 2 is very, very suspicious, because, you know, all it takes is somebody reporting a compressive strength test as a you know, undrained shear strength, or all it takes is somebody reporting something in TSF and KSF. So I think there's a lot of avenues to introduce an error by a factor of 2 in that type of testing. And, you know, we basically went back and said, hey guys, can you go back through your procedures and try to weed this out? And to the lab's benefit, we haven't seen that again. Those 2 projects were very close together. So I'm almost wondering if it was a operator error where maybe they had a new person that was going a little too fast with how some of that data was being recorded. I don't think it was the wrong measurement. I don't think it's a discrepancy in the actual soil. I think the lesson learned there is, you know, we can have errors in the data, and I think the engineer, you know, it's ultimately, as the engineer, it's our responsibility to kind of interject ourselves somewhere in that process where we've seen the samples or have at least had some opportunity to inspect the samples, and at least from a big picture say, look, I looked at all those samples and they were all stiff clay, and in a stiff clay, I should not have a capacity of this. You know, nothing, you know, I'm not saying all our engineers need to go run all the tests, but I think to start to develop that hands-on understanding of this is what a stiff clay is, and this is what a soft clay is, and not to be just looking at numbers on a sheet of paper. That was kind of the lesson learned there, because I really think I think it was a a transcription or reporting error and not actual discrepancy in the value.
Thank you. So we have a question about time for static load tests. As you noted, you normally test 2 weeks after installation. Do you ever perform your tests out beyond that 14 days?
We typically don't, because contractors don't like that. We have done that for research, but to be honest, we've actually pushed them up. We've pushed them up earlier. I'm a big fan of pile setup. I'm a big believer in pile setup, and so in my opinion, it's just points on a graph. Like if we know what we're doing and we pay attention to when the time delays, as far as I'm concerned, as long as we have enough data to build that setup curve, then we can move those tests to wherever. And not speaking of static load testing, but just some of our restrikes, we'll do a 15-minute and a 1-hour restrike as opposed to going back out to a site and doing a 24-hour. And that's something we've been very interested in is, how can you push the limits on where you place those tests to make things easier on everybody. But to answer the question, well, so Eric says he's a contractor / engineer, but we typically don't push them back because our contractors typically don't want us doing that. And so the 14-day, I think the 14-day makes everybody happy. They try to do those load tests during their assembly period. And so I think they've got very a lot of things depend on getting those knocked out where they're not trying to wait on static load testing during any kind of a critical path part of the schedule, so we've pushed them back, but only for research, not in any kind of attempt to say, okay, I hope we see higher capacities here or something like that.
Robert, do you have any recommendations on reset intervals, or do you make recommendations?
I'm with Jesse, and probably don't. The more, the better. And if we can wait longer, great. In design build, the bigger projects, you tend to have a little more flexibility, or you hope you do, to work those in to wait longer. But that you become then a small piece in a bigger ship, and but we've tend to like getting as much data as we can as far out as we can conceivably do. I didn't see any other questions come in. I was going to piggyback on Jesse's thing about getting field engineers more involved in the sampling and collecting. That's something we see a lot. And I know there's probably several big firms on here. The smaller firms, it's easier for the geotechs when they're newer to get out and get that experience. But if you don't have it, and DOTs, it is an issue sometimes. You don't have that experience, and you need to do that, figure out how to do that. And if you're a supervising manager, get your people out, because understanding what happens can help you identify some of those things, and also gives you that, ability to have that judgment later that, oh, well, yeah, this is how we're supposed to handle these samples. Oh, they didn't handle it that way. There's our 2.
I have a question about the large diameter pipes. 3 foot is the limit, or the lower limit of a large diameter pipe. What do you think about 2 to 3 foot diameter pipes? I mean, I see those more commonly, and I think they're sort of like open end, but how do they? Is there a trend which way they fall?
No, and I meant to say something like that about that, but I don't want to run out of time. These terms we use, like large diameter pile. Okay, I'll even throw it out. When is it a micro pile, and when is it not a micro pile? We've got micro piles that are macro size, but it's a tooling thing. Or when's a drilled shaft versus an auger pile? There's always going to be some gray area, right? And so even those 24s could behave more like a large diameter pile where it doesn't plug or does plug. And I think that'll be soil dependent. But we're talking, the diameter's getting smaller, right? So we're getting closer and closer to, it's going to behave like a solid pile almost regardless, or it's not. So I don't know. I think it's going to be another one of those, like Jesse said, we don't deal in yes and no's, right? And I'm going to use that, by the way, a lot now. I like the way you phrase it. I've said it so many other ways, but I love the way you phrase that, Jesse. That's good.
I go for it. We can make it into something here,
Yeah, and especially contractors and owners. You being the owner, you don't like, you're a little different since you're the owner's engineer, but you don't like being told, hey, wait.
One more question about the open-end pipes. You mentioned unsuccessful application of a constrictor plate. Do you know of
Yeah.
or one that didn't plug the way it was meant to? I guess that's how I interpreted it.
Yeah, and I meant to pull that case study back up. Maybe you're familiar with it, the one that Kentucky did, and I don't know if anybody from Kentucky's on the call. I don't think so, but yeah, I don't recall it being super successful. They may have had some, varying success. We haven't seen a lot of attempts at that, and it, especially in design build, sometimes you have these great ideas at the beginning, but then as it starts to get closer to actually building it or finish the design, it's like, well, that's going to be too much schedule risk, or that's going to be, we want to do this, but we can't. And we just accept the get closer to yes or no. Yeah, let's just do it the way we know it'll work versus, this might work out good for us. So I don't know. Yeah.
Are there any guidelines for the openings that you place in the constrictor plates? The size of them, or
not that I've seen.
Okay.
I think it's too new of people trying it. So any professors on the call? Sounds like a research project right there.
Well, I think we are almost out of time. So if anyone has any questions, you could squeeze it in here in the next minute. And if not, I'll note that this webinar is every other month on the third Wednesday, same time. So our next webinar will be November 15th. And Dr. Rick Kaufman, hopefully will be back from his out-of-country work and present on pile foundation subject to liquefaction and down drag loading. And yep, we're about out of time. No more questions. So thanks to everyone for attending, and hope to see you in November.
Thanks for having us. I appreciate it.
Greatly appreciate it. Thank you, guys.
Thank you so much for the time, both of you, Robert, Jesse.
You're welcome.